Hello everyone, my name is Deyan Wu. I'm a third-year PhD student from X-Discovery Lab at Dallas College. Today, I'm going to talk about Capacitivo, content-based object recognition on interactive fabric using capacitive sensing. This work was done in collaboration with two undergrad interns, Lu and Yuji, as well as my advisor, Teddy and Xing-Dong. Before going into detail of this work, I want to briefly show you what Capacitivo is and why it can be used for. Capacitivo is a capacitive sensing technique that makes fabric aware of the objects it's in contact with. This includes things like food items and dinnerware. It can also detect the change of what's inside objects like containers or cups. For example, it can differentiate between milk, Coke, apple cider, cold and hot water in a regular glass cup. And as many everyday objects around us are made or covered by fabric, there are numbers of applications that are enabled by our sensing technique, such as turning a coaster into a delta tracker with our smart textile, or a smart tablecloth for recipe helper.
Next step, add a slice of cheese.
Although there are a number of techniques to enable interactive fabric, the one most related to Capacitivo is Textiles by Xing-Dong et al. Textiles demonstrates an interactive fabric to recognize metallic objects based on inductance. In contrast, our work focuses on non-metallic objects that are also very common in daily life. Our work complements existing research with a new sensing technique that is based on capacitance. Next, I will explain how the sensing works for Capacitivo. When an object is placed on a textile sensor that is made of conductive electrodes, the capacitance among the electrodes will change due to the permittivity of the object, and the different material of the object will bring out different permittivity, resulting in different capacitance. Thus, Capacitivo recognizes objects by measuring different changes in capacitance. And next, let's dive into more detail of the sensor design. Our sensor is composed of diamond-shaped electrodes that are connected by rods and currents, and there's a ground plane on the bottom that is similar to the common design of touch panel. With this setup, there are two types of capacitance occurring on the electrode. They are mutual capacitance and self-capacitance. Mutual capacitance is the capacitance between the adjacent electrodes, and the self-capacitance is the capacitance between the electrode and the ground plane. Both are affected by an object. To allow the signal more pronounced in response to the small change in capacitance, we use a resonance-based capacitive sensor to precisely measure the aggregation of them. However, this approach is problematic. The sensor reading at a location interferes with all electrodes connected in the same row or column due to self-capacitance. To solve this problem, we also measure the mutual capacitance to capture the content area of the object, and then we gather the sensor reading only in the content area. Next, we need to determine the proper size of the electrode and the separation distance between the electrodes, which are two factors that affect sensor sensitivity. Thus, we conduct two experiments. In the first experiment, we test the electrode with a size of 7 mm, 14 mm, 21 mm, with a fixed separation of 2 mm. The results are revealed in the left side of the table. Clearly, 7 mm is the best option among three sizes, considering the balance between the sensitivity and the resolution. And next, we conduct a second experiment where we test the separation of 2 mm, 3 mm, and 4 mm, and a fixed size of 7 mm. The results are shown on the right side of the table. Surprisingly, the separation of 4 mm is the best option, since it increases the sensitivity significantly, but without largely impacting 2D resolution. Thus, through these two experiments, we determine the size of 7 mm and the separation of 4 mm for our implementation. Next, I want to talk about our DIY approach for fabrication. First, we're using an unarmed adhesive to bond the conductive fabric to a textile substrate. Then, we use a textile cutting machine to cut out the electrode and the rod connection. After cutting, we reheat it again, and then peel the unnecessary pieces off. So the pattern is clear. Next, we need to connect the coloring electrodes. To connect the coloring electrode, we're using a sewing machine or hand stitch to connect the conductive thread for each color. Then, we attach a conductive fabric to the bottom as a ground plane. The sensor is completed. Then, I'm going to describe how we accomplish object recognition using the textile sensor. When an object is placed on the sensor reports a 12 by 12 capacitance values. Based on our observation and the initial test, we extract 86 features, which can be divided into two categories: shape-related feature, like the number of cover pixels, and the material-related feature, like mean and median. After the feature vector is packed, we then feed it into a random forest model since it has been found to be accurate, robust, scalable, and efficient in many applications. We use the output from the model as our prediction results. In the following demo video, I'm going to demonstrate our sensor working in real time. The detected item name will be shown on the left side of the screen, and the heat map image of the capacitance footprint will be shown on the right side. We can detect different types of objects, like those in an office, such as hand sanitizer, AirPods, lipstick, hard drive, credit cards, and another credit cards. We can also detect the objects in a living room, such as candle, book, a water plant, and a water plant. We can also detect the glass and detect if the water is in glass. We can also detect the object in a kitchen, such as a bowl or a bowl for soup. We can also detect the slice of cheese, salt, and we can also detect the multiple items. And even different type of liquids. To validate the sensor accuracy and the robustness, we ran a 10-participant study. We tested 20 everyday objects, including kiwi, avocado, grapefruit, credit card, and so on. Each object was repeated for 10 times in a randomized order. We pre-trained a model 3 days before the study, and we ran the real-time recognition in the study. In turn, our system can achieve overall accuracy of 94%. This is an encouraging result, especially for the items which have a similar shape but have a different content or material, such as kiwi and avocado. In addition, we also evaluate how well the system can recognize different types of liquids. For this evaluation, we recruit a volunteer and asked her to test 6 types of liquids, including cold water, hot water, Coke, apple cider, milk, and beer. Each drink had 20 samples for training and 20 samples for testing. The results show the overall accuracy of 90%. The worst case, which was beer, if removed, resulting in a higher accuracy of up to 96%. Aside from this test, we also tested the performance of the sensor in a vertical placement similar to a pocket. The process is the same as the one described previously. We had 1 volunteer and 20 samples for training and testing. We include 8 objects can be put into the sensor, such as AirPods, lipstick, kiwi, avocado, cheese, Discovery credit card, JCPenney reward card, a book, and an external hard drive. The overall accuracy is only 70%, which is likely because our sensing technique is contact-based. When the sensor is placed vertically, the contact between the object and the sensor cannot be guaranteed, since the object may partially lean against the sensor or due to the deformation of the sensor itself. If we remove the least 3 performing items, the accuracy can rise to 87%. In addition to the application shown in the beginning, I want to show you some more demo application of our sensor. For example, if we integrate with the IoT speaker, our system can remind a user to take a lipstick left on the table. When a user registers or shop at a website for the very first time, the tablecloth recognizes the credit card placed on it and automatically fills in the credit card information. Further, the tablecloth can also detect if the user table plant is in need for watering, so the user can be reminded when the soil is dry. Finally, the system can remind the user to clean the table after the empty bowl used for soup was left on the table for several hours. Next, I would like to discuss the future work. First, our preliminary results demonstrate the sensor deformation still affects the sensor reading. We are investigating the method that can model the shape deformation of the sensor using the unique sensor reading introduced by folding the electrode at different location, degree, and angles. Second, as our technique uses capacitive sensing, it is expected that a finger touch gesture can also be sensed. However, our current prototype had a frame rate around 3 to 4 Hz due to the hardware limitation. In the future, we plan to improve the hardware, making the prototype even support touch input. Third, our technique cannot differentiate metallic objects. This is a limitation of capacitive sensing. We expect that a hybrid approach combining capacitive sensing with inductive sensing has the great potential to solve this problem. With that, I would like to conclude our work with 3 take-home messages. First, we present a non-metallic object recognition technique on interactive fabric using capacitive sensing. We measure the accuracy of our technique with several experiments. We demonstrate unique application enabled by our sensing technique. Thank you for taking the time to listen.